turn sound off right now? Good evening. Happy Tech Tuesday. This is Chris, and we're at the TGH's Crawlers Clubhouse, and we're going to talk about a little bit about motor talk. We're going to talk about why we select what we select and why your decisions matter. There's nothing worse than spending $1,000 on your truck and not doing what you want it to do. So we're going to get into a few things. So before we know why we select our motors, we got to have a basic understanding about how they work. So basically, we're going to start off with brush motors, and we're going to talk about rebuildable motors first. There are rebuildable motors, and there are sealed cam motors. So what we have on the screen over here, this is the core of a rebuildable motor. This is what we call the armature. Or in this case, because it's fully assembled, I would call it a rotor. Maybe that term belongs with brushless motors, I don't know. But when we break it down a little further, though, Hoss, would you click on the end bell for us, please? Or, no? You'll have to scroll to the left here, pal. Keep going. See your bar down here, boss man? We're new.
No, go down to the bar. The bar on the bottom, the little pictures. Yeah, right there. It's a slide.
Is it not up there? There you go. All right, there's an end bell. So the end bell then goes on the back side of the can. There it is. Yep. Now let's go ahead and front us an assembled 400. Probably over here to the right, buddy. That's not a 400.
Yeah, see it.
One more. You'll get there. Let's get rid of that. Yeah, we're gonna switch. We're switching drivers. Be patient. Okay. There you are. Thanks, Mikey. All right. So what we have here is we have the can, the motor can. This is a Puller 400, which is just slightly smaller than your standard 550 can. Nonetheless, we're more worried about the components that the can houses, right? And that's why that's how we're gonna keep from burning up our electronics. That's how we're gonna gain that low end control. You guys following back there? So let's break it apart. Mikey, go ahead and go back to the armature. Let's start with this one right here. Yeah. So this armature right here is a machine wound armature. It is a 5-slot, which means the iron core, which is a stack of laminations, has 5 slots, which create these poles, right? Or rather, these cores, these wire cores. So at any rate, you see the holes there? That's balancing. We'll get to that in a little bit. On the end here, this is an isolator, and this is what we call the commutator. So Mikey, if you go to, there's a picture of, yeah, there you go. Make that big guy fit the screen there. We'll have to work that out. So here you have these brushes. The brush is right on the commutator. So on a 5-slot motor, you also have 5 slots in the commutator, right? And then I'll go back to that brush. I better just stick to my script here. Got sidetracked. So Mike, if you go back to the brush hood, please. Thanks, buddy. So this brush hood goes on the back side of the can. So when your armature slides into the can, this is what captures it. You have a lock ring. These are brush channels, spring posts. The red you see over here, that is a brush hood. There's a black one here. You can get those. These particular ones are anodized or coated rather, so that these are actually aluminum, so they're probably anodized and so that they don't corrode. So those go between the brush channel here, Mikey, and the end bell. Go ahead and click on that. Right here, you can see that. So when we talk about brush channels, let's start. Now we're going to get into some technical stuff here. So when we talk about brush channels, there are 2 types of brush channels. There are what is pictured here is a stand-up channel, and then the one next to it here, Mikey, right here. stand-up channel. The one to the left is a lay-down channel. So what that means to you is it's the orientation in which the brush rides on the commutator. You cannot take a stand-up brush and put it into a lay-down brush hood. These brushes are curved, if you will, on the mating surface of the commutator. So when if you decide that you might want to swap those out, you might want to know the benefit of that, right? So what you're going to end up with is more drag brake and more RPM, or more voltage overall, right? So more voltage contact overall for a given point in your throttle band. Let's see here, go to the springs, Mikey. So the springs are what's going to hold our brushes in, right? So there they are right there. So these come in a couple different, probably many different tensions. I know of a couple. Keep in mind, all this information is available out there. This is not anything new. I just did a little bit of research, and I've been taught a lot of things from a lot of cool people. So I'm just sharing that. So these springs, you'll notice, like on the Holmes Hobbies website, you can get a motor that is double X, right? And so the coil wrap of the spring doesn't change. The dimensions, or the lengths rather, of the spring itself, none of that functionally changes. The wire diameter changes. And so a double X spring is a little bit thicker of a wire when it comes to the spring, so therefore it has more spring tension. So what do you get out of that? A stronger drag brake, right? Let's go ahead and go to that armature, Mikey. Let's talk about armature for a minute. So armatures come in a variety of different shapes and sizes, if you will, really. I guess they're all cylindrical in fashion, but definitely different diameters and lengths, right? Not only that, they come out in different style cores. So this is, again, that 5-core we were looking at that was machine wound. This is a hand wound 3-slot core. And then is there a picture in there somewhere, Mikey? It was slotted. I don't see one. So nonetheless, there are 2 more variations of this that we particularly focus on and use. One is a 5-slot skewed armature. Mike, you can pull one up on Google and drop it up there. So, and then a 3-slot skewed armature. So one thing you'll notice on this screen here, though, is these little drill points here and this epoxy here. So what you'll find on your sealed can motors, hopefully, is that it's that subtractive balancing, right? So they're locating that heavy spot, and they're removing material until they get the armature unbalanced. So on this side here, this is a much higher quality motor, and here they're doing a epoxy balance. So that's a dynamic style balancing as well. They'll add additive balancing, I suppose. So speaking of which, though, when we talk about the windings, and we said machine wound and hand wound, one other thing you'll notice. Anybody else out there notice it? Give you just a couple seconds. There's a particular difference between the windings in these 2 armatures.
One doesn't look like a bird's nest.
One doesn't look like a bird's nest. That's a good point to make. Right? Machine wound, hand wound. Significant difference, right? What else? Anybody on there? Anybody on YouTube got us?
Nope.
So what about look at the quality of wire? Not only the quality, but look at the diameter of wire. So although you would not wrap this, well, I suppose you could, but you would not likely wrap this 5-slot core with thick, what Holmes calls triple X wire, right? Or double X wire, 13 double X. So the 13 double X is the thicker wire. Thicker wire offers more heat resistance, and more efficiency. That's the primary use for that. Anybody out there know what the problem with drilling these armatures are? Why would we think about what we're doing here. What are we achieving with these motors?
IRB.
High RPM. Well, one knob at a time for this guy. How about you, Mikey? Ask that question out there. Anybody know what the disadvantage of these two little drill spots is or are over this epoxy?
Resistance to airflow. You're actually going to have to work harder because you're going to draw air into those.
All right, so let's break it down real quick before we move on. What does a coil winding wires do when you energize it? What's it create?
Heat and magnetic force.
It connects. It creates a magnetic field, right? So it creates a magnetic field. This core. Hold on, Mikey. Hold on, buddy. This core creates its own magnetic field. Think about it like a circle, like this, right? Down the axis of the core. So down the axis of the core, it's got a circle of a magnetic field. So what happens when you put a magnet next to it? Two things could happen. What could happen? It could either push it towards it or pull it away, right? Hence rotation. We just house it between a bunch of magnets, right? So when we drill these holes, that magnetic field is disrupted because those laminations are shorted out against one another. So no disruption in the core, a much higher quality core as well. Pretty nifty, right? So what would that mean to you? Efficiency, right? We talk about crawling one knob at a time. Let's crawl one knob at a time. So the commutator, well, like I was saying earlier, will have equal amount of slots for each one of these, as well as a 3-slot. So what that ends up happening for us is, if we lay our brush down sideways on this thing, that's hit that X button. That's K and K. Close it out. Turn that volume down, please. Apologize for that. On the end here, we have an insulator, right? On the outside of that insulator, you'll have shims that shim the motor. Okay, Mike, if you go back to that armature picture that has the this one right here. Yep. And get rid of that. Yep. So these here right here are shims. So isolator and shims on both sides. So we talked about that magnetic wrap around those cores, right? That motor wants to center in the center of those magnetic fields that the permanent magnets are holding. So a DC permanent magnet motor, okay? Versus a brushless, which we'll talk briefly about. I don't play a lot of brushless. I've learned a lot last year and a half, but those magnets spin. If it's an in runner, it spins inside the coil windings. If it's an out runner, it spins on the outside diameter. The housing spins. So at any rate, so this motor is going to want to center itself in the housing. Okay, hence the reason there's a little in play in most of your drivetrains. So on these rebuildable motors, Mike, would you pull me up like maybe the Crawlmaster or something like that? Yeah, put it just by itself there. There we go. So this particular motor is a 5-slot, hand wound with neodymium magnets. Up here at the top, you'll see hash marks on the side of this. Those are timing marks. Okay, so a motor that spins faster in one direction than the other. And let's assume we're talking about like perfect conditions, right? Your radio's all zeroed out, everything arms perfectly. You apply a few volts to this thing and it spins faster in one direction than the other. That is a timing thing. So neutral timing is when Mikey got fired. So neutral timing is a condition where the motor RPMs are the same in both directions. Copy? So then if we advance that timing, we increase the RPMs in one direction, right? So before you switch over your battery leads, if you ever your power leads, your motor power leads, before you swap them over, if you ever have a condition where it's faster in reverse than forward, make sure your radio is zeroed out first and foremost. And if it's a rebuildable motor with adjustable timing, then set the timing to 0. You'll get the lowest no load amp draw out of that. So the more you advance the timing, the more amp draw you put on the brushes. Okay. So that Crawlmaster motor or the Holmes motor, the stubby, either one. You just pull them up like that, Mike. That's fine. There you go. These guys are going to run double X springs. That helps improve the drag brake. Double X springs, of course, with active drag brake these days, right? You know. So why does it matter if a motor? There we go, Mikey. So why does it matter if a motor's got 3 slots, 5 slots? Why does it matter? What does that mean to us? Right? We talk, you listen to me ramble on about a little bit about the motors and what you're looking at, right? What the pieces are and the parts are. So why does it matter to us if we run a 5 slot or a 3 slot?
Well, the 5 slots would run cooler.
Cooler? My 5 slot's way cool. No, why does it matter to us? So we talked about the magnetic field that the armature makes when we wrap a coil of windings around it, right?
Work.
So inside the can is two permanent magnets. They're 2-pole motors, right? And this kind of segues into brushless a little bit. But they're 2-pole motors, north and south, 2-pole, right? So you have 2 magnets creating opposite forces, or maybe it's the same force, I suppose. And each one of these is creating a magnetic field. So is it gonna, depending on which side of this you apply the voltage. So depending on which side you apply the voltage, positive, negative wire swaps, right? Makes the motor go the opposite direction. That's because you're reversing the polarity of the magnetic field, and it makes it spin. So if I only have 2 magnets, where's those dry erase markers at, Mikey? Let's get into this a little bit.
Whatever color you want, buddy.
Oh, hose you.
J.
So if we have a magnetic field around, can I just go to paint or something? Just a white screen. Go to paint. Go to paint.
I'm working it out. Give me a second.
So we draw a can. Inside the can, you have your magnets, right? They kind of look like this. Bam, perfect. Everybody follow? So then if we have a 3 slot, then we have they make this circle in here, right? They meet, right? And so we wrap this core with wire. It creates a magnetic field. It spins around, right? So the more of those slots that are in that armature, the smaller they are. The smaller they are, the less force naturally was like at a given voltage that they'll have on the motor. Hence the reason for a smoother startup on a 5-slot motor. So this has a magnetic field, and I don't know how to draw it, and this has a magnetic field. And they push away from each other. Hence we rotate, right? We get that rag, Mikey. What did I do with that rag, pal? I just had it.
It's in the front sand strip.
So with pull that 5-slot motor back up, please, sir. So with a 5-slot motor, a smaller magnetic field, it picks up sooner on the magnetics, right? So one, you have a smaller iron core, therefore you have a smaller wire wrap, so therefore you have less pull. And the way it picks up the magnets, if you have more of those, it will pick it up sooner and later in the rotation, if that makes sense. So you have one magnetic field fighting against another one, so on and so forth, and it creates that smoother startup over the 3-slot motor. Then you take it a step further, and where this starts, are you going to make that? Go ahead, Mikey. Make it full screen for me, pal. So if you have a magnet here and a magnet here, and they're putting out their polar opposites or opposites attract. Nonetheless, watch stuff like you get that rotation, and this one's picking up before this one leaves. So even though this magnetic field's pushing, that one's pulling, they're working together, or maybe they're pushing together. That's the story for John Holmes, that whole magnetic field stuff, right? So we talk about gearing and ratios and startup and all that. That's why it matters. That's why the brush slots matter. What else can we talk about with that guy? Where are we at on time, boss?
Oh, we got plenty of time.
Oh, plenty of time. Good. So we take this 5 slot, and we put a skew on it, so it comes off of here.
He's got a skewed armature one we could throw up there.
Oh, he does?
Yeah.
I'll throw it up there. Yeah, although not our preferred motor. Maybe a few too many windings. 37 slot motor. I bet it's got great startup at about 3,200 RPM.
Yeah.
So,
but it's still skewed. So
yeah, so you can see how these slots are skewed. So that's going to further advance that drivability of the 5 slot motor. So you take a 3 slot, you take a 3 slot straight motor armature. Grab me the 3 slot there. They leave them up like that, just like that. Not since we're dealing with the same 2 magnets. The cans are the same, although not all magnets are equal. Let's be clear about that. You have further distance between your magnetic fields. There comes a cog. Right now, these 3 slot motors are excellent efficiency and gobs of torque, right? Yeah, the lower count you go in motors is only relative to the same armature, right? To the same style of armature. So they say lower turn count, faster motor. It's only relative to the same armature. Okay, because winding counts, there's so many factors that come into that. Magnetics, poorly manufactured armatures, right? Machine wound versus hand wound. You take the same 2 motors, the same windings, the same count, one machine wound, one hand wound, and they're going to be completely different. Okay? They also make the 3 slot skewed, which is kind of where we started, wasn't it, guys? 3 slot skewed. Those are that's going to improve over your Torque Master Expert, the white can motor. Let's see here. What else do we want to know about motors? So we talk about. I hear a lot of people asking about what turn motor should I get. Okay. Mikey, there's a file on my computer that you could email to Haas, and it is called Holmes KV. It should be in a recent documents, and then you can put that up on the screen. So given an understanding of why things start up smooth. So cleaners with this one, the preceding magnet or the forward magnet is going to pick up. The forward core is going to pick up the magnet before the other one exits, right? And so it kind of goes back to that 5 slot principle where you have more of those that are traveling through that magnetic field. Give you that smoother startup. So the further you advance, you get smoother startup, right? So a 5 slot motor is going to start up way smoother than a 3 slot motor. So at any rate, we're going to jump into why it matters to us. So what's KV? What is KV? How does it matter? Why does it matter? How do we keep from burning up our electronics? How do we keep from smoking motors? How do we keep from buying just the wrong application, right? Putting a motor in the wrong application. Can you find me anything yet there, Mikey?
Trying to.
So at any rate, KV is basically, it's for every volt applied, you get that many KV in RPM, theoretically, right? So a 2,700 KV motor will yield 2,700 RPMs, 2,700 RPMs per volt. So you ever see on a motor where it says 50,000 RPM max? Do you ever wonder why that matters? 50,000 RPM max. Well, if I over apply voltage, it's going to exceed that RPM limit, right? Because it's for every volt of DC current from your LiPo battery applied. Did you not get there, Mikey? So we'll do it like this.
I got you. It's coming.
All right. Well, don't pull it up just yet. Now we're on to something else. So that's primarily how brushless motors are expressed. Our friend John Holmes has got a chart on his webpage that expresses those KVs. I have to read it backwards. No, I don't
Write
want
it
to.
backwards. 'Cause it's backwards.
Oh,
on the
it's
screen.
backwards on the screen.
Yeah.
I am not writing it backwards.
Yep. You are.
We'll have to fix that. So if I have a 2700 kV motor and I apply 10 volts to it, what's my maximum RPM? 27,000 RPM, right?
Backwards.
So that goes to, oh yeah, that's backwards too, buddy. No, it's not.
It is on
It is
Oh, on the screen it is.
when you do it.
Bummer. For 2700 kV. So we take the kV times 10. Can we get that off the screen, please, buddy?
Yep.
Maybe put a motor back up there. Pull that over to the other screen and work on it. There we go.
Why?
So 2700 kV, 10 volts, 27,000 RPMs, right? So if your motor had 50,000 RPM max, you'd be just exceeding that at 20 volts. So that would be what, 5S? All right, 5 times 4, 1, right? So you wouldn't want to run a 2700 kV at 50,000 RPM max on a 5S battery, right? Same thing applies to the Holmes motors. So for example, a Trailmaster Sport 550 12 turn is 3,000 kV. So that's easy numbers. So we take 3,000 kV and we say that it's going to be at full throttle 3S, that'd be 12.6. So 12 times 3, what did I say, 3,000? So 36, yeah, 36,000 RPM. So we're good there. So that's our max revolution on our motor, 36,000. Oh, it's backwards, huh? 36,000 RPM. So what's our ratio? How do we know if we're going to cog that motor down? How do we know if we're going to burn up our electronics? How do we know what temperature is acceptable for electronics? We know what temperature is acceptable because we read it, right? That's the only reason I know. Well, that I've smoked plenty of things, but I couldn't tell you what the temperature was, right? But 180 degrees for 6 minutes, no problem. 160 degrees all day, full send, right? The hotter, keep in mind, the hotter your stuff runs, the less efficient it's going to be. Okay. So we're back to this 36,000 RPM. If I have a reduction, did we get the mirroring thing figured out?
That's what we're working.
All right.
Don't
So
you worry about it.
because I'd like to write it on the
What we
screen.
write isn't backwards to them.
Huh?
Perfect.
They're saying what we're writing is not backwards to them.
Oh, you guys are awesome. Perfect. All right. So we're 36. Is that what I said?
36,000.
Yeah, it's 36,000. 36,000. Sorry for the technical difficulties. We are new. We just want to share the information we got with y'all.
Well,
So you can
backwards
make-
on my screen.
Yeah. So you can make educated. Bro, I'm in the middle of a live stream. Yeah. Yeah.
Say hi to the internet.
And why don't you just go on to YouTube and watch? Hey, I harass you during your live streams. It's okay, pal. Later. Sorry. That was Josh. So 36,000 RPMs, right? So if we take what we know, what do we know? So let's take a too low, for example, right? We're you see that there, guys?
Mhm.
So good. So we're a 10 tooth pinion, call it in a 62 spur at 6-1, right? What else are we? We're 2.6 on the, 1.9, 2.6, 2.6 on the rear output. And then what are we? Depends, right? Are we straight axles or are we portals? Okay, this is why it matters. This is how you burn stuff up, right? So transmission, what do you got, Mikey?
One each.
What's that? What's this multiplied? Can you give me that? 2.6 times 6. It's going to be like 14 some change, right?
14.2.
I ain't. Nope.
Right.
14.2? Is that right? It's 14 something. I know that for a fact. So at any rate, 15.86. See, I know that for a fact. That's what I get for I listen to you. I'll call the guy that drew the thing up. How about that? All right. So if we take that and then we have an axle to think about, right? So we have an axle to think about. There we go. Thanks, buddy. So our axle, if we're just going to talk standard box stock stuff, what are we at? 3 point. Spit it out. Come on. 3.75, right? So 3.75 times 15.86. What are you got going on here? You're killing me. Check that calculator, not that one. I don't, pal. Yeah, slightly.
Works fine.
What's your answer then? I'm trying to talk, buddy. I don't want to run a calculator.
Yeah, we
19-1. That is not right.
Gate.
Okay.
Restart.
How about we do that?
Refresh.
Here we go.
flew over.
Do over. Can I get a mulligan?
Replay.
Mulligan. Jeez, oh Pete. All right. So much for winging it. All right. So we're 36,000 RPM. We've got a ratio of 6-1 in this ring and spur, right? Or pinion and spur, right? Then we have a ratio of 2.6 to 1 to the output. $15.6. Take our 15.6 and we multiply it by 3.75. 58.5. So that's our overall final ratio at the wheel hex, right? That's our final drive ratio. So then we take our 36,000 RPMs and we divide it by our final drive ratio. My RPMs is 620. So you take the final drive, divided by your 3,600. So every 36,000 full throttle, 620 RPM at the wheel hex, right? So your motor's 36,000 RPM. Your hex is 620 RPM. Does that make sense? You cheering on that? All right. 620 RPM. This is where they get into that rollout stuff, which your motor choice can help with that. You can keep from burning your motors up with that as well. What size tires you running? That's a wheel. 1.9 is a wheel. What size tire you running?
475.
475, right? So Haas, what's your time?
You got 25 minutes.
What's the circumference of 4.75? How do we find that? Diameter times pi r squared, right? Times diameter. Pi r squared times diameter. So, no, that's area. That's area. So we're going to take 4.75. We need the diameter.
It's not on the sheet.
It's not on the sheet. Not on my cheat sheet. But
It's not on your cheat sheet. It's not on your cheat sheet, but it is on your cheat sheet. It's at the bottom. Pay attention. Welcome to class. We're trying to not burn up our motors, right? We want to learn how not to burn up our motors.
it is on there.
Oh, it is on there. Imagine that. So we need to know the diameter of 4.75. So we take 175 divided by 2.
You let people know you're taking questions. Nobody's asked anything.
Yeah, I mean, I'll take a question. Yeah, of course.
Nobody's asked anything.
That's okay. That's because they're too busy laughing, bud.
Well,
We've been well prepared. So that's our diameter. We're gonna times that times 3.14. Christina, did you double check that? Where'd it go? Bear with me here. I apologize. Bless you.
6.5 inch.
So you have a 6.5 inch. You have a 4.75 diameter tire, right? So you have to do diameter times radius squared. Is that right for circumference? I'm pretty sure that's right. Times 2.08.
The circumference of the circle multiply the diameter of the circle.
Yeah. So do that for me. Diameter. That circumference is diameter times pi, right? So what we're trying to figure out is,
3.146.
yeah, so that's how fast our truck's going to go, right? We're trying to gauge our gear ratio over the diameter of the tire, the circumference of the tire is how fast the thing's going to travel, right? I typically walk behind my trucks, right? So we want that low end startup, that low end crawlability, right? So the KV of the motor matters for that. If we have if we have too high a KV motor, then we're spinning things too fast, right? We're putting too much of a load on there if we don't have enough reduction, right? So the more reduction you have, typically the higher KV motor you can get away with. The 13 turn, for example, what's the KV rating on the 13 turn? It is Puller 400, 13 turn, 1700 kV. So that's a super fast motor, right? No, super slow. The Puller 400 13 double X is 2700 kV. So that'd be like picture a 2700 kV brushless motor in your crawler. It'd be pretty fast, right? It'd be a nice trail rig.
Too fast.
Too fast for sure.
2700. That's like a 413 turn.
So 620 RPMs at the wheel hex. You know, if you have a larger diameter tire, it's going to be that much faster, right? Which is going to put more strain on things. No, it's going to create more torque. It's like another gear out there, right? Think about it. Right? See it? At any rate.
Hartley's tuning in on his way home.
Oh, boy. Harley, I'm failing miserably, bud. I got my audience is in the house is heckling me. Yeah, failed miserably. So if we talk about, let's see here, what else we talk about? Timing. There's the brush motors that are rebuildable, which we went through the different components of those. Being able to select the different slot choices, right? How that's going to affect your startup. So the more slots, in theory, you'll have a little bit better startup. Reduces the amount of distance between magnet and magnetic field, right? The two magnetic fields, one for your magnet.
Cogging.
Yeah, cogging, right?
Yes, cogging.
Less cogging, that's right. We talk about torque and efficiency. You're gonna get that out of that 3-slot motor. If you want to go to the ultimate startup for a brush motor, you're gonna go to a 5-slot, but it's gonna be that skewed one. That Mikey, what was that 37 slot you showed earlier? Don't spare us, right? But like I was mentioning, don't overlook the windings. If you have a high geared truck, right? Like it's easy to burn up electronics and generate heat if you're overloading the amp draw on the motor. That motor is going to pull as many amps as the speed controller will allow it before one of them lets go, right? And when we have something that we need lots of power, gobs of power for, we want to go with a higher turn, less count armature, less slots in the armature. It's going to give you more torque and more efficiency for that, right? You wouldn't get the same strength out of the magnetic fields in a 5-slot because there's less iron core, there's less energized wire around less iron core, right? They don't intersect. We talk about brushless motors. There's in-runners and out-runners. So an in-runner motor is one where the stator or the magnets are spinning inside of a energized case, if you will. So inside the case, there's a series of windings in there that are, take the DC motor, the permanent magnet motor, and you replace the motor windings with magnets, and you replace the magnets with motor windings, right? And so the magnets are then attached to the shaft, the output shaft, and the output shaft therefore rotates. We talk about an outrunner motor. This one, we talk about poles. Go back to that. Let's talk about poles of the in runners real quick. No, the in runners. Yep. Nope. This guy right here. So you hear often a lot of times about revolvers being a 14-pole motor, or you've heard John talk about the 6-shooter, right? Or you've heard about 4-pole motors. Okay. Well, remember I said when we were talking about the DC motors that the magnets were, it's essentially a 2-pole motor, right? North and south poles. So on the 6-shooter, there are 6 poles. Okay. So in the armature of a brushed motor, we have the slots that we wrap our windings around. The rotor of a brushless motor is the magnets with those slots in it. Okay. So there are no brush contact. So there's no tension on the commutator. Remember the copper piece there with the isolator on it, the isolator washing? There is no spring tension on that with brushes, right? There's no transfer of energy there. It's solely based off of magnetic field. Without the addition of applying the wires get energized through the can, basically, right? You have your 3 phases, A, B, and C. So if you go to an outrunner, though, pick me an outrunner, Mikey. There's one in there somewhere. Yeah, so this outrunner motor right here, the outer shell or the outer casing, as you've seen them spin, right? They spin. That is attached to the output shaft. The difference between that and the inside, or excuse me, an in-runner, is that the magnets are on the outside, which cause they're on the casing, if you will, and it causes the casing to spin, right? So because the casing is attached to the output shaft, remember the windings of the brushless motor are stationary anyway, whether it's an in-runner or an outrunner, they're stationary.
Does the extra voltage of 4S and 3S create more heat and decrease efficiency over the duration of the run with these comparisons?
I would say no. No. If you're so 3S and 4S application.
Asked my question or not, what the question was, but
yeah. So the question was related to heat.
Between 4 and 3S.
Yeah, between 4 and 3S, and so the voltage is linear, right? That's why we use a motor controller. That's why we had to kind of like set a base sample at the beginning. It's linear, right? You have a motor controller, you have a speed controller, and so you're gonna get. I think you're gonna get more efficiency on a 4S battery when it comes to the position of the throttle within the controller. If you took the same exact setup and you put, identical, and you put a 3S battery in one and a 4S battery in the other, the truck is going to move sooner with a 4S battery, right? Because the sweep and the throttle. And maybe it's more involved in that, but that's how I look at it. I think you get more efficiency out of a higher voltage battery. The term is gear down, volt up, right? That's for a reason. So we were talking about RPMs, 620 RPMs. If I build a truck and I tune a truck to 600 RPMs, like we were talking about on this, and I run it for 6 minutes and I pull it off the course and I can fry an egg on it, something's going on, right? I got to troubleshoot that. I pull my motor pinion off, make sure my drivetrain spins smooth. I got my motor pinion off. I feel what my motor feels like, right? Okay, motor and drivetrain both feel good. I put the motor pinion back on. I know I got no binding. So I am overloading something somewhere, right? Too much drag on the electronics. So 620 RPM on a straight axle, no portal, you're going to run higher temperatures on your gear than you would say so you had your ratio, your output ratio, add another 1.9 to that, and you have that much more reduction, right? So if I had 1.9 worth of reduction in my portal and I had a 22575 tire in place of my 475, am I gaining anything? Right? Tuning, right? So what I could do is if I could go down in KV, right? Go down in KV, get more torque out of a lower KV motor, right?
His response is, so it's only taking what ESC gives it despite the voltage.
Yes, it only takes what the ESC gives it despite the voltage. I wish I could show you the video of the SCX6 on a 2 low and a 1400 kV snub nose with 180 amp ESC. That was cool. So it crawled great until I squeezed the throttle and the little motor that couldn't. So it only gives what you supply it via the speed controller. So the sealed cam motors, as far as the brush ones go, those aren't rebuildable. Those you can't adjust the timing on those. On these brushless motors right here that are censored, you have censored and sensorless. Right, sensorless motors are going to be, as far as an end runner is concerned, is going to be more geared towards. Yeah, there it is right there. So that's a 6-shooter. That's a sensorless. That's a sensor. There'll be a harness wire that goes in the back of that. That's a Hall effect sensor in there, and it tells the speed controller where the motor is within its magnetic field, essentially, to dumb it down for people in my terms. And you get a much smoother startup. Now, somebody I know has done wonders with magnetics on a 6-shooter, right? And those do well. The sensorless ones do well as either. The technology's coming along. If we could omit the sensor wire and still get the same performance, then why wouldn't we, right? When we go back to brush motors, I keep going back to brush motors because that's typically what you're going to see burned up. That's where you're going to generate your heat. And it's basically overloading the amp draw on the motor constantly. Right? You're asking the motor to do more than it can. We talk about the poles on the brushless in-runner. You hear 4 and 6 poles, which you typically hear, right? So a 4-pole motor. Go back to that in-runner, Mikey. So think of the poles as like slots almost, right? Except for on the opposite, because we know that the slots are what spins. So on your stator of an in-runner, you have your circle. That's a terrible color. Okay, you have your stator. These are your magnets. There's your 4-pole, right? There's your 4 poles of your magnets on your stator. Or your rotor, rather. Rotor. My bad. Rotor. Do-do-do-do. Think of stator as stay still. Rotor as rotates. So that if you had 6 poles, it would be like that, right? So then we take an outrunner motor. Mike, can you throw an outrunner up on the right? We take an outrunner motor and we talk about the poles, the 14 poles that I mentioned earlier. So in this circle right here, right, remember, in a brushless motor, the windings don't spin. Where in the DC motor, they do, right? There are magnets. 14 of them. I guess there's more than 14, right? There's 14. No, there is 14. 14 poles. So those are the different poles. So that's why with you can get better startup out of this sensorless than you can this sensorless. Right? There's more poles. Same as it applies to 3 and 5 slot motors. Right? We got to get John to start skewing his magnets. Right? There's one for you. Skew him. No, probably wouldn't work. So let's talk about what motor do we want for our application. Are we crawling? Are we running through mud pits? Do we care? Do you care? I don't really care, but Mikey cares. So is it a submarine? Right? Are you going through the mud pits? Are you rock bouncing it? Are you dragging something with it? Are you technical rock crawling, or are you just trailing all day with a 12-pound rig? How much does your rig weigh, right? If you're going to be bashing your truck through the mud and stuff, I would highly suggest a seal can motor. They're inexpensive, right? They're not rebuildable, and for that kind of application where it's go, they do the trick. If you're going to be trailing every day, I don't recommend a 5-slot skewed motor, for example.
28-pound all brass TRX4 is what Harley's driving.
Oh, I built it for him.
Yeah. What motor is setting up for you putting in that?
Is that what he wants to know? What motor? I would highly recommend the SCX6 factory electronics for that one. So what motors do you put in stuff, right? If you got a 7, 8, 9, 10 pound trail rig and you're running straight axles, AR40 style straight axle, AR44 style straight axles in a 3-gear transmission, if you want your electronics to run cooler, then you're going to want to gear down, right? They're going to run more efficient that way. Go to a 3-slot motor. It's a more efficient motor in the first place. It's got more torque, right? If you're not happy with the startup of the 3-slot motor, you could go to a 3-slot skewed, which is still can get machine wound or hand wound, and then you could go to it's just going to matter. Now, if you're on a comp rig, you want that exceptional startup, right? So you can start with a 5-slot motor, make your way to a 5-slot skewed motor. And then from there, it's like, how high end do you want to go, right? Hand wound, machine wound. Most 5-slot skewed motors are hand wound. They tend to be your higher end motors, 5-slot hand wounds.
What about a 28 pound? Too late.
Yeah. We're going to put the SCX6 electronics in it. We decided. So anyway, it was a rough live stream for me. I appreciate you tuning in. I did my research, but I got sidetracked. Imagine that. Shocker. Anyway, if you have any questions, post them in the comments below, and we'll get to them as soon as we can. Thanks for joining me.
Yeah, 5 minutes to answer questions.
So that's about it for us. Bottom line is, when you're selecting your motors, you need to have an understanding of how they operate. And when you increase the slot counts and decrease the windings, they're going to generate more heat. And those they come with a benefit though, and you need to understand that. They come with their variants of startups. And this is all assuming a perfect world, right? You could theoretically calculate all that stuff. Take what you know and improve from there, right? You saw the pictures of the hand wound versus the machine wound and the difference in the quality. That's a difference in efficiency. That's a difference in startup. That's a difference in power and torque. And really, that's all we got for you at the clubhouse. So thanks for watching. The next one will be better. It'll be as good as the first one. This one was terrible. Thanks.